I've just joined the CRADLE project, which is robotics in demanding and long-lasting environments. So we look at robots in pretty much from very kind of connected Cradle's just starting. Continuing with the project, we're looking at many different environments. Okay. Understanding how these environments may all be an extremely challenging environment because bulky and very representative of an environment. I'm Dr Mohamed Atia from the University of Manchester. I work in the robotics and environment. Our reason for line up is to explore this as an example of an extreme environment that we might My current project is actually for nuclear environment, where the reason that there is high levels of radiation. Not quite different than a lot of similar challenges from what we're involved in, like unstructured project terrain, dumps is also everyone else to do various different environments. Yes, I understand. How the family line up. Because we've got a commercial facility lined up that
Right. Okay, everyone. Good afternoon. Good afternoon. Good afternoon. So, welcome to the first public and live edition of the CRADLE Talks Robotics Research Seminar. We're going live in public, and this is going to be recorded in YouTube. So, welcome, everyone. We have a lot of audience in Teams. So, my name is Paul Beniket, by the way, academic and technical project manager for CRADLE. And today, I just want to have a bit of script that I prepared. So this is CRADLE Talks. It's a series of seminars and discussions highlighting the research and relevant cases for CRADLE. CRADLE, what is CRADLE? If you are new, CRADLE stands for Center for Robotic Autonomy in Demanding and Long-Lasting Environments. And it is a 5-year EPSRC prosperity partnership between the University of Manchester and Jacobs. So, CRADLE aims to empower UK and global industries with advanced robotics and autonomous systems. So to know more, you can visit our website, cradlerobotics.co.uk, or our social media channels. Well, today is a very special day because we're approaching our birthday, or our first year anniversary since project kickoff, right? And we've seen a lot of the team grow. And for this day's edition, we have 3 presentations from our new starters. We have Dr. Danish Khan, who's our robotics technical specialist. We have Dr. Kwai Wa Tse, who's sparse guy, who's our software technical specialist. And then we have Mohamed Atia, Dr. Mohamed Atia, who's our postdoctoral research associate in work package components, or work package 1. So, to facilitate the discussion, so we'll hold any questions until the end of the talks. And for those who are online or in Teams, please type them in the chat. And for those in person, you need to go up in front to ask your question, if that's fine. So we're not moving around the space. That's fine. Okay, I don't want to delay anything further. To go with our first speaker, we have Dr. Danish Khan. Yeah.
Thank you, Paul. Thank you very much.
Oh, sure.
Yeah. Okay. So, hello everyone. So I'm Danish. So I joined CRADLE as a robotics technical specialist. Before joining CRADLE, I was working at the Australian Center for Robotics at the University of Sydney. And before that, I did my PhD from South Korea, Kyungpook National University. So the work I'm going to present today was part of my PhD. And the title of my presentation is Single Shot Active 3D Sensing Based on Stereo Vision and Adaptable Speckle Pattern Projection. Okay. So stereo vision is not the only method of 3D sensing, but it is safe to say that it is the mainstream method of acquiring 3D geometry of scene and different objects. So in stereo vision, we have two images, either taken from one single camera or two different cameras from different views. And then we establish correspondence between both images and do the triangulation to estimate 3D points. So, although it looks very easy task, but it is not straightforward. We can easily match the points with distinct features, for example, corners or the objects with specific spatial properties, but it fails in homogeneous region. It struggles to find correspondences with textureless or smooth region. So there is a lot of chance the algorithm get confused with wrong points because the digital value is almost similar in those regions. And so once we have that disparity after establishing the correspondences, we can estimate depth using this equation. So one way of solving correspondence problem is projecting light-coded patterns on the object, and which helps basically in solving the correspondence problem. And there are a number of different methods of encoding the light. So some people use color coding, or it can be a fringe projection. There are different type of methods depending on the algorithm. The main idea is you apply the image correlation, and there are two basic type of image correlation, spatial or temporal. So in spatial correlation, you have using the epipolar geometry, the images are aligned, and you do the one-dimensional search, and based on the window, some correlation metric like sum of absolute difference or similar to these, you can find the correspondence based on small windows patches. And in temporal correlation, every pixel is encoded using a series of patterns. So there is a trade-off between accuracy and time, computational cost. So a single spatial correlation requires only one image or single shot. So it is a very fast method, but accuracy is low. In contrast to temporal correlation, where it requires multiple patterns, the accuracy is really good, but you suffer from movement-related errors due to the slow sequential speed. So the main motivation of this work was to exploit only one light pattern and get the maximum accuracy from that pattern so that we can get rid of movement-related errors. And typically, the projector is very large and contains very complex optical components. And one motivation was to make it small so that we can fit in multiple robotics application, and to find a stereo matching algorithm that works better for that specific projector. So before showing the system, I would like to mention the phenomena, how speckle is generated. When a coherent laser light is passed through a diffuser or rough surface, due to the interference of light, so it on the observation plane, so it a kind of a spot, dark and bright spots are generated, which is called speckle pattern. And it's when we take image of that speckle, it depends on various factors, like the size between the diffuser and the observation plane, the illuminating area of the laser, and the wavelength of laser as well. So you can see we can create speckles with different size by changing the distance between the diffuser and the observation plane. So based on this principle, we proposed a system that used that speckle pattern, and we took help from that pattern to solve the correspondence problem between stereo pairs. So the cameras are synchronized, time synchronized. They capture the image at the exactly same time so that there are no motion related errors. And we use that pattern to solve the correspondence problem. So the idea is you apply feature detection on left image using Shi-Tomasi feature detector, and then track these features in right image. Once we have that correspondence, we can do triangulation between both to get the 3D point because the cameras are calibrated. We know the intrinsic and extrinsic parameter of the camera. So why KLT? Because it works very well with gradients of high magnitude. So laser speckle provide that, but there are two constraints of KLT. The motion between two images should not be very high, and the brightness should remain constant. If there is a difference between the brightness, the features will not be tracked. So one challenge in that was sparsity. So, you can see when you track good features or individual features, not every pixel is a good feature. So you cannot get very dense point cloud. So I took this image of my hand with the pattern and did the triangulation. These are the point cloud, and this is the 3D mesh generated from the raw point clouds. So the accuracy is good. The accuracy was good. There was no wrong matches, but the data is very sparse. And other challenge was non-uniform pattern. So, because I was not using very complex optical configuration, it was a simple setup, a diffuser and a lens. So, you can see the pattern throughout the object is not uniform due to the Gaussian effect of the optical system. The speckle at the center, the frequency is very high, and around the corners, it is not very visible. So in contrast to a commercial DLP projector, so, because it used complex optics, very high frequency LED light, it was very uniform. So I tried adding more optical components like this flat top diffuser. This is a device used to randomize the frequency of laser speckle, but there are side effects. So it reduces the laser power. And so this was not enough to establish the correspondence. The brightness in the digital images was so low due to this. And one more challenge in designing this system was that the laser speckles are subjective to camera. Even there is a slight variation in the aperture of one camera. You cannot establish the correspondence because the constraint of KLT was the brightness should remain constant throughout all the frames. So you have to manually adjust the aperture every time carefully, and that was very hard to do. So I use image processing to deal with this problem. The first step of the pre-processing was image histogram matching. So after getting a histogram of both images, apply matching. So this will solve the subjective speckle problem. The brightness is, you can say, somewhat matched between both the image. So after histogram matching, I applied edge preserving contrast enhancement using Laplacian filters to kind of tackle the non-uniform pattern problem, and then apply KLT feature tracking. So in this way, I was able to track all the pixels, not just sparse points. So these are results from some of the acquisition. So you can see the brightness difference when the aperture is not carefully set between the cameras. So when there's a difference in aperture, it can totally disturb the depth estimation process due to the difference in brightness. So after applying histogram matching, I was able to get the correspondences even if there is a large gap between the aperture. So this is the effect of applying edge preserving contrast enhancement. So it kind of solved the non-uniformity problem of the speckle pattern. So this is the test I did to compare the density of my system with other methods. So I compared the density with Connect version 1, which kind of use a very similar procedure. It projects a random pattern and calculates the 3D geometry. And this SLS 3D is a professional 3D scanner. It requires more than 50 patterns to calculate the geometry. So you can see there is not much difference in the density, although my system used only one pattern. By the way, this model look very good because it is a complete reconstructed model acquired from capturing different multiple short patterns and then doing the 3D registration between all the acquisition. So this is a complete 360-degree model of the object. Okay, so now up till now we have only talked about the fixed pattern, but there is one problem associated with the fixed pattern. So when the object distance changes, the speckle size changes due to the diffraction of light, and KLT algorithm require an optimal speckle size. And there is because it works based on the window matching, so there is a trade-off in choosing the window size. If you select a large window, it is more robust, but takes more time to do the calculation. And if you select small window size, so it is less, although it takes less time, but it is not very robust. And window is selected based on the size and scale of the features being tracked. So when you change the distance of the object from the sensor, the speckle size on the object changes. So every time you need to adjust the speckle size. So to solve this problem, we proposed this system. The working is very similar to what autofocus do in our camera. So it measured the distance of the object and then changed the position of the lens to make the object in focus. So this is kind of a feedback loop. So we calculate speckle size in real time, and then based on the distance of the object, the position between diffuser and the lens changes to retain the same optimal speckle size, even if the object distance changes. So this was the first step. You can think of it as a calibration. So as the diffuser was mounted on a linearized motor, and it has 30 steps. Each step was of 0.5 millimeter. So I calculated the speckle size at each step of the stage. And you can see as the distance is increasing, the speckle size is reducing. And this was the optimal range analysis to decide the optimal position of the diffuser based on the object distance. So it was decided based on lowest reprojection error and highest number of 3D points. Roughly the optimal position of the diffuser shift 4 to 5 steps forward for every 20 centimeter of the object. So this is how I calculated the optimal position. And you can see the difference in result. So with the fixed pattern, initially the pattern was set for 110 centimeter. And when I moved the position of the object to 50 system, the depth was not very good. But after adaptive pattern, the system adjusted itself to maintain the speckle size, and I was able to get better result. So I did a lot of experiment to calculate the measurement accuracy. This was one of the tests where we acquired the 3D geometry of a flat object and fit to the standard plane and find the deviation between the standard plane and the 3D points. So my method was better with single pattern compared to others, multiple and single shot patterns. So in conclusion, so I will say that when we want to use only one pattern for 3D reconstruction, a laser speckle can be a good choice. And in presence of noisy image, we can use KLT tracker to solve the correspondence problem. And instead of making a complex optical system, we can use image processing methods to get better results. And in this study, we conducted experimental analysis to investigate the impact of object distance on speckle size and 3D acquisition. And we proposed a system that automatically maintained the speckle size in real time. Yeah. So thank you all for listening.
Well, thank you so much, Danish. So we'll quickly move on to our next speaker, and then we'll put the questions later on. So that's fine. Thank you.
Facilitate. Welcome to the CRADLE Talk this afternoon. Good afternoon, everyone. And I'm Sky. My name is actually Kwai Wa Tse. It's hard to pronounce. That's why I have a funny name called Sky, but it's not a legal one. And yes, I want to stand more closer to my audience because my voice is quite low. And I'm from Hong Kong just 3 months ago. Yes, I'm new to the UK. And the topic I'm going to present today is, okay. I'm afraid I need to facilitate the online audience because yes. And my topic is AI-powered UAV-based inspection systems for crack detections, localizations, and quantifications. Quantifications means measurements, size measurements of the cracks. And so basically, I will present 3 topics and 3 publication work this afternoon. But don't worry, I'm trying to make it simple, okay? And yeah, this is my agenda. I will introduce myself with the educational background. And following that, I will select some of my research work. Actually, it's not only limited to the work presented this afternoon. I have other extra interesting works, yes. And this Jones, comes with me with the pictures here. And this Jones is very important to me during my PhD study. That's why I bring it from Hong Kong to the UK. I sacrifice a lot of shirts, jackets, and my kids' toys I need to sacrifice. But this one is a must. Yes, okay, for my educational background, I obtained my bachelor degree 11 years ago, 2013, from the Chinese University of Hong Kong. And actually, my background comes from computer science. And after 2013, I go to the industry, work for three years. And then I realized once I have problems, I have to ask the university. So I jumped into the university again for my master's degree. And I obtained my master's degree in 2018. And luckily, I got the distinction award. And at that time, my supervisor said, oh, this kid got the potentials. Are you interested to join my research group to have some cool stuff, to make some cool stuff? And I said, why not? Okay, that's how I start my PhD. I don't know what's your story, but this is mine. Okay, my supervisor is Professor Wen Ziyong. He is a well-known chair professor and the department head of the AAE department. AAE is the Aeronautical and Aviation Engineering. And my supervisor's PhD, he do it in Caltech in the States. And his story is about working on the last 6 seconds landing vehicles on Mars. So amazing. And he had trapped me and seduced me to the PhD degree. Okay, I believe this is a very famous quote and has been quoted by many people that if you can explain something simply, you don't understand it well enough. That's why I will try to explain my research ideas in a simple way. Okay, this is my research backgrounds. And we have a lot of large bridge in Hong Kong. This one called Hong Kong Zhuhai Macau Bridge. It is 55 kilometers long. And I believe sometimes accidents happen and the train or the large boat will crash on the bridge. And this one is a terrible accident in Guangzhou. Just 3 months ago, a large boat crashed and broken the bridge. And in this case, we need to do an emergency inspection, right? But if we can fly a drone there, it's more efficient, right? Okay, this is the overview of the 3 works I'm going to present today. And I can shift this toy to you have a look. And my research topics are covering three major domains. First one is detections. I use the neural network models to detect cracks, defects on the large infrastructures, especially on large bridge, a very large one, called Harbor Bridge. And secondly, I will localize the defects with relative positions of the cracks and the zones. And what's next is measurements. I want to measure and estimate the size of defects of interest. So the domain knowledge covering detection, localizations, and we can do some advanced dynamics for the movements of the zones. And later on is the segmentations and quantifications. Okay. This is the first one. As you may know, it's quite difficult for you to fly a drone in the real world because you need to follow rules from the government. You need to compile the assurance and verifications, make sure safeties don't hurt people, don't hurt the infrastructures, and also you need to have a pilot license to fly the drones in the real world. That's why here you can see I'm using banners to mimic a real bridge in this way, a side view of the bridge. And this is the software architectures of that hardware systems. I have only one onboard computers, it's Jetson TX2 for the online real-time calculations and detections for cracks. And this drone has a depth camera D455, the RealSense one, for the depth map and the RGB image for crack detections and localizations for both. Okay, here is visualizations of my detection models. It can successfully detect and generalize a lot of cracks. As you can see here, this is the real-time image from the vehicles. It's not offline versions for detections. And the model I use the YOLO backbone. And actually, this work was conducted in 2022. At that time, YOLO V4 are still not a very old one. And based on the backbone, I changed it and I tailor-made, customized a lot of modules for it to push its performance on the detections. And as you can see, the performance of the detectors for cracks are almost 90%. 90% MAP, it means that the mean average precisions. Talking about the detections, we are not meaning that this is 90% correct. No, it means that sometimes we have false positive, sometimes we have true positive. This matrix means that the true positive over the true positive plus the false positive. So 90% for a lot of different types of cracks are actually is highly accurate. Okay, I will try to examine my models further. So I joined a conference in Poland last year in June 2023. This is UAV competitions about detections of defects, and I got the first place for these competitions. Yes, as you can see, on the right-hand side is the drone doing the inspections in a GPS denial environment. And the left-hand side are the real-time detections, fully on board and autonomous for the crack detections in this way. On the left-hand side, this is the neural network models and the architectures. I will skip the details of each component here, but I want to highlight that my data sets include 30,000 of crack images, contain different types of and shapes of cracks to train the neural network models for the fully autonomous inspection systems. Like this. This is just a glance of the cracks. And what is the novelties of this work? The novelty is I put attention mechanisms into my model. If people want to improve a neural network model, in typical, there are three methods to improve the model. First one, you need to increase the depth of the neural network. For example, you make a larger model, you have a large, high computational computer to train it. This is one way. And the second one is you can tune the level parameters in different combinations, try to have a higher accuracy. And the next one is you can put some attention mechanisms on it. What is attention mechanisms? Actually, like human beings, when you come into a room, you have pictures on the scene, but you cannot fully concentrate on all different single component, right? You may put your focus on one single thing. For my personal, maybe, oh, there's a beautiful girl. I will put my attention on this beautiful girl instead of all this 20 audience here, right? So this is the attention mechanism. I want my model focus on little tiny cracks on the large buildings. I don't want anything else. I just focus on cracks, please. This kind of things. And on the left-hand side is the original YOLO reform model. The web components here is I add the mechanisms in these components to increase the performance. Okay, what is attention mechanisms? Actually, it just suppress the things you are not interested and enlarge the things you are interested. So you need to multiply factors for the original input. Okay, this is the original input channels. And then you differentiate in different colors with different weights and use the weight factors to multiply the original one to become, this one is the output instead of the original input channels. Okay, the second one is localizations. How to localize the crack? I believe all of you are the master of transformation, right? It's just a simple transformations. The U and V is the image coordinates of the crack from the YOLO detectors. And then you convert the pixels coordinate into the real world coordinates through the camera coordinates. Simple, but beauty, right? Just very simple. You just convert the coordinate into a real coordinate for the localizations. And at the end, I achieved the accuracy within 100 millimeter, just like this. I mean, you fly a drone, that large drone, to a beach, and detect a crack into a wave like this, the accuracy, within 100 millimeters. Yes, sometimes actually the crack like this size, so 100 millimeters is good enough. Maybe for some professional industrial equipments, they can do it in maybe several millimeters with acoustic sensors or lasers, put a lot of payloads on the vehicles. Yes, actually the performance will be within 100 meters. But for a single computer vision technique, 100 meters is quite good. Okay, after you detect the crack, what's next? You can add some strategic movements on it. And this is the second work. There are some objects here, like a traffic light, a boat. Typically, they are on maybe they will on the beach or in the infrastructure. And then once the drone detects the object of interest, it can perform some movement like this. It's a circular movement for the traffic lights or the boat. But this red point means that there's an obstacle behind the object. Don't go across it. So you can add this kind of movement or trajectories for your inspection. Okay, this one is the computational analysis. For this single onboard computer, I use TX2. The performance of real-time detections is about 10 frames per second. It means that you can, in 1 second, you can have 10 infections or predictions of the cracks. It's good enough for the real-time performance. Okay, after we detect it, and we can have a precise localizations of the defects, what is next? I'm trying to give some data analysis or scoring assessments on the cracks, but we still need some components. That component is that the 3D models of the target, the inspection target, and what is the predetermined path. So we need to figure out the complete inspection coverage path for the whole infrastructures. First one you need is you need to create the 3D models of the infrastructure. The LiDAR I use is the LiftForce 360. As you can see, we can fly a UAV with a small payload LiDARs to the beach, and then you can acquire the 3D models of the inspection target. And then I use the viewpoint generations algorithm to generate many viewpoints of the cameras. These arrows here, it means that there are single positions of the cameras for the inspections. And then we can generate a fully coverage path like this. This comes with a minimal distance for the inspections. We call it traveling salesman persons problems. Just we need to travel the viewpoint with minimal distance. And before I carry out all the view flights, I do it in all the simulations to make sure the safety is low collisions and it has a complete fully coverage for the inspection systems before I have the view flight. Okay, here comes the main contributions of this work is if you want to estimate the size of cracks in traditional detectors, normally the output will be a rectangle in pink color. And in the traditional bounding box method, this is the width of the crack, and this is the height. But it's not precise, right? The real width of the cracks will be in yellow color one, and this one is the height of the crack. And that's why we need segmentations. Segmentations actually is a advance of 2D detections. It means that segmentation means that you need to classify these pixels belong to the quack log on the pixel level, not on the object level. But for the object detection, you just have a view on the whole image to detect whether it contains a quack log. But segmentation method is it originally used for tumors, the X-rays with tumors, but human eyes cannot easily differentiate whether it has a tumor in the X-ray image. That's why we did segmentations. And then I trained segmentation called ULED with spectral and attention mechanisms. We call it USSA-LED segmentation models to have a precise semantic mask on the quacks. After we have the semantic mask of the quack, we can do some computer vision analysis. For example, like we can calculate the longest horizontal physics of the quack and the longest vertical physics within the quacks. And besides that, we can also have some called minimal rectangle area algorithms to give smaller rectangles instead of the YOLO or other detectors. They will be in the pink color. The pink color is not precise as the green color rectangle method, but you can only use the green method with segmented image. You cannot do a diagonal rectangle on the 2D detectors. That's the motivations for this segmentation work. Okay, after I have a precise segmented image of quack, I can estimate the real size of the quacks within 10 millimeters. This is the estimations, comparisons with the ground truth. GT means the ground truth value, EST means the estimations and measurements of my model, and ERR means the error. I achieved the errors within 10 millimeters by my segmentation model. Yes, that's the end. Thank you for listening. Okay.
Thank you so much, Sky. We've got some questions on the chat, so if you're still on Teams, you can address that, both Danish and Sky. So thank you. Now, next we have Dr. Mohamed Atia, so take it away, 15 minutes.
Hello everyone. So yeah, as you know, I'm Mohammed. So I'm working as a postdoc on CRADLE project. I'm working package 1 component. So yeah, so I'm working on package 1. So currently I'm working on the modeling of underwater robots. So where I am trying to model and understand the behavior of non-linear hydrodynamics of the water, and how can I model system to to estimate the behavior of the robot. So I did my PhD in the University of Nottingham on soft robots, and this is what I'm talking today. So first, I'll talk about an introduction about soft robots, then what was the contribution of my work, and what is the concept of this soft robot that we developed, and modeling, shape optimization, and at the end, demonstration of this kind of robot. So first, what is a soft robot? Yeah, we all know soft robot is like any robot that consists of rigid elements. No, this is not a soft robot. This is the traditional robot. So what is a soft robot is? Soft robot is consists of soft or flexible elements. So you can see here on the left side, most of the conventional or the robots we see here or commercially, and every one of them they try to make it, or like try to, if we can make it soft robot, what actuators or what will behave or what it would look like. Yeah, moving on. So to control this soft robot, or how can I build this soft robot? To build this soft robot, I need something called soft actuator. By its name, it is soft. So soft actuator is actually something, or an actuator or transducer that converts energy from one form to another, from either electrostatic energy, like DEA, as you can see here. It can be using sheet metal alloy, using heat element, or it can be using fluid as fluid elastomer actuator. So all these sort of actuators are they are being used soft, but still they are not as robust enough as the DC motor or the real actuators we see in conventional robots. So here is my work come, where how can I improve this actuator? How can I improve the robustness of the soft robot so that it can be used and it can improve the system, or how can I use it, implement it in real life and like in commercial situations. So first, the real motivation of the work was the lack of reconfigurable or the lack of modular soft robots. So the main novelty of my work was developing this building blocks or these modular reconfigurable soft robots, and to build them I need to understand the behavior of them and how can I make them robust enough, how they behave. That's why we have analytical modeling or numerical modeling. Then we have validation, we have experimental validation, then we have shape optimization. If I have this model and yeah, it's valid, it is accurate enough, how can you use this model to actually build a robot? How can I design it or manufacture it to have this shape, for example? That's why we have this shape optimization strategy. Then we have a natural or bio-inspired grasping technique. How can I grasp something, taking advantage of this soft robot? Yeah, at the end, we also have the demonstration and showing the capability of this modular system. Yeah, so as you can see here, so the system is these modules on the top. You can see it consists of almost 8 elements. It consists of number 1, DEA, the electric elastomer actuator. So what is DEA? So the DEA, how it works, is almost like a sheet of, let's say, rubber or hyperelastic material, like rubber. So it is coated with carbon electrodes or flexible electrodes. When you apply high voltage to them, like 5 kilovolt or 6 kilovolt, the charges of the electrodes, they try to attract each other. So they generate strain. So they make the rubber sheet expand. So the way you implement it in the manufacturing, adapted to the manufacturing, it can change the bending, the strain, or so the expansion of the system. So that is the main principle, and how can you implement it? So yeah, we have DEA, we have electrical terminals, because you need to connect all the elements of the array of this modular system together to actuate them simultaneously. We have number 5, meteorods. Meteorods work as like the backbone of the system, where you can actually charge this strain of the backbone. So while you actuate the system, the backbone is behaving differently. Yeah, so we have number 7 and 6. We have the snap fit to mechanically connect all the elements together. And number 8, we have electrical terminal. So this is to connect them electrically. So how actually we build or manufacture them? So first we have the structure of the building block, which is linking cap and meteorod. We have this DA. We stretch it first. The way it works needs to be stretched. So we stretch it in the 2 directions. So we have lambda 1 and lambda 2. So these two parameters, we'll be using them as parameters of the model later on. So we switch them, we wrap them around the structure, and then we leave them to relax. So when they relax, they will generate this bending angle as in number 5. So this bending angle, when you actuate this building block, this bending angle will change. So based on that, you will have a behavior of the robot. So based on having one building block, you can see on the left image, in the middle, we can snap them together, we can rotate them together, so we can assemble them into different configuration of robots, such as the fun trunk, or the bio-robot, or mobile manipulator. Sorry, soft manipulator. So this is a quick video of how actually simple and fast these building blocks can be assembled into a configuration. So on the left picture of this sheet, we have we want to do shape optimization for this convex concave object. So based on the optimization told us you need to have this stretching ratio, this length of the building block, as this diameter of the knit rod. So based on that, we have these numbers, and then try to using these numbers to extend them. So using the snap fit, the terminals, they are all connected together as one element. Very long video. So also they can be assembled. So if we have manipulators, they can assemble to the system. Same thing, they can, like the assembly, it can be also assembled. Speed up the video a bit. Yeah, so this shows the advantage of this quick assembly as an advantage of the system, which it should soft robots be. If we have this advantage system assembled, why can't use full advantage of it? Back to the slides. Yeah, so modeling. So yeah, we have analytical modeling, we have numerical modeling. Why do we have both? So the problem that system is nonlinear. So if I am using only analytical model, it is not accurate enough. So I need to have some sort of, I need to understand the system first before actually modeling it. So that's why we were using finite element for the numerical modeling. So first I was using just one building block and try to simulate it and try to understand it and try to change the design parameters. D is a natural diameter, lambda 1 is a stretching ratio in x direction, L is length of the entire building block. Using this, I can understand system. So also on the adaptable modeling part, we have the energy method where we can understand system in equation, because you need to use the model at the end, you need to control it. Or numerical modeling will take at least 30 minutes to run one case. So you need something fast, something quick that you can use reliably. So this is only for the modeling of one building block or one module. If I'm having something like elephant trunk, so using the robotic kinematics, I can have this entire model of the entire robot. So what actually does the numerical modeling look like? So in this video, so we have an actuated state, So this is the DA will be stretched and then it is wrapped around the surface, and then is relaxed now. Now it is being actuated, applying pressure or high voltage. So it is expanded, or like the bending angle changes. So this model was validated against nine or more case studies, and the average error was around 5.8%, which is around like 1.5 degrees. So analytical modeling. Of course, analytical modeling was less accurate. Error was like more than like 12%, but we had to do optimization and tuning of the parameters so that we can have a bit more reliable. So we ended up with error of around 7%. So if the first equation is a model of one building block, which you have the student energy. It is based on the energy method, so we have the student energy of every element. We have the student energy of the electrodes, we have the student energy of meteoroids, and the potential energy of external loads that is applied to the system. Also it works for multiple building blocks or entire robot assembled together. So now we have a model. How can we use this model for generating or building an entire robot based on the knowledge we have to have that? For example, if we look on the top, so we have on the left that shape, this elephant trunk shape. How I can use this building blocks and the model to have, I need to use for every element, or for example, I need 16 building blocks, and first one needs to be manufactured this way. These design parameters for second one, third one. So how can I have this? From the middle, you can see we have the modeling of one building block. We have lookup table of 84 cases because we can't keep the numerical modeling running because it takes time. So using the lookup table and robot kinematics, we can have the model of the entire robot, and then we use optimization to generate this configuration. In case if we have on the bottom, if we have constrained environment, for example, if I want to build a soft manipulator, which it needs to conform to an object, like a strawberry, for example. So I still have this constraint optimization where I can have this shape contour as a constraint, and I'm building my optimization to not collide with it, but like only conform and surround this object. A case of this optimization is this convex concave object on the top. So this object, the weight of this object was like 18 grams, and the recovery manipulated, you see on the bottom, you see, so I have right fingers and left fingers. So first the left fingers are like open, then go down, and then closes. So then advantage of the system, it grabs, or like it surrounds the object, so it's power grasping. So instead of having only one point of contact, I'm having a surface of contact. This is an advantage of the system. So if I have a different object, I will run optimization again, and I will get these building blocks, which will generate the shape that will conform this object. So every time I can just have another object, I disassemble the fingers, an optimization, assemble the fingers again based on this optimization output, and then grasp it. So this was the bio-inspired technique. So here is some videos of the demonstration to show the capabilities of the system. This is, so this is the convex concave object. So now the back fingers are open, it goes down, it's actuated again. So, and the front fingers are applying force to the system to ensure it is actually grasped correctly. So this is the first demo of the system. So what imagine if I want to grasp something more delicate, such as bread or gingerbread. So and this video is split up like 4 times or something. 4 times. So now it starts with the 4 walls. Then like what about the trunk I was talking about all day? So shape like this, it is like a bit similar to elephant trunk. So it's actuated, it opens, then it approaches the object. Now this surrounds the object, it is unactive, it is deactuated. Now it's approaching the placing position, and then someone needs to pick it up. Now it opens, it's actuated, so it opens, and then it goes back to its location, and now it is unactuated. So what about actually a mobile robot? Yeah, so using the control of the gate of the 4 legs, we can make it run fast. It wasn't that fast, to be fair. I can't remember the speed, but it was, this is like 7 times. It was like 20 millimeters per second, 15 millimeters per second, something like between 10 and 20 millimeters. So these are actually similar to just the soft fingers, but just flip upside down. And so this demonstration actually was done after 5 or 6 months of the gingerbread house assembly. So these are the same fingers used in gingerbread house, used after 5 months. This is just to prove the system is still reliable, it's still working. The efficiency, yeah, it became like it decreased at least 50%, but yeah, it is still working. And it's low-cost system, so it doesn't work like every building block it works like 1 quid or something. Not much. Yeah, thank you.
Thank you, Mohammed. So thanks everyone. So unfortunately, this is we're ending the stream right now. But for questions, I've booked the room until 2:30, so have to. So you can still continue the discussions. For those people who are online, you can type in your questions, and I'm sure Danish, Sky, and Mohammed would be able to answer it while we are here. But thanks again for coming, and see you on the next Cradle Talks. Right. Cheers. Thank you. Cheers, everyone.